start with state preparation, perform some unitary evolution, and then measure. Yeah, so we have time symmetry for this unitary evolution. However, we treat the boundary conditions in a different way, asymmetric way. But the physics is believed to be symmetric. So maybe we could make it more symmetric. Yeah, so that's the idea. So if there is a process for state preparation and we live in symmetric physics, maybe just reverse this process, perform the same but reverse at the end. So here you have preparation and you have postparation, the same but reverse. Yeah, so here we enforce a initial state. Here you should enforce the final state. So for example, for silicon quantum dots, a state preparation is performed one of settings through just impulse to make the electrons tunnel. So let's just use a reverse impulse at the end, and from perspective of symmetry, we perform exactly the same state preparation process. Yeah, so in many situations, the state preparation is performed by electromagnetic impulse. So let's just use reverse impulse. Yeah? So that's reverse the shape of the impulse and use it at the end. And you should be able to enforce not only the initial state, but also the final states. If being able to do both, you should be able in theory attack problems and get more stable, more error resistant quantum computers. So it could pour new fuel to quantum computing. Yes? So I will try to convince you that in many settings it should be possible and what are the consequences. Yes. Okay. So here is the some history. So generally we believe that physics is symmetric. So the question is, could we apply it somehow to improve computational power, for example? And yes, so this is an example trying to literally apply the symmetry of physics. And so I do similar ideas as one of many main directions for like 15 years. And finally, a year ago, I have started this article, and then with Pavel will be the XPRIZE team, and we have 40 interns, and there are a few articles later I will later mention briefly. So there I also talk about some indirect arguments, experimental, but finally the next step will be a direct experiment. So we are searching for a collaboration with the direct one. So one direction is taking such quantum computer, for example, superconducting silicon dots, and trying to literally in the controller apply the opposite, the reverse impulse at the end, and try to use it as state preparation, but the reverse version. Yes. And there are a few experiments with lasers I will talk about. So if somebody could help, let me collaborate with. So if successful, it would make quantum computers much more powerful, more stable, and in theory attacking problems. Okay, so what is the CPT symmetry? So the CPT symmetry is believed to be at heart of modern physics. Quantum theories, which are Lorentz invariant, local, have to be CPT symmetric. So it is necessary for modern physics. And it says that performing this charge parity and time transformation, the equations of physics should be the same. Yes, so if you perform setting, it should behave the same. Yes, so there are some asymmetries, especially in the entropy growth, but like in this lake, which is fundamentally symmetric, you can drop a rock, and we have fundamentally symmetric equations, but asymmetric solution. So often the asymmetry is in the solution, not in the equations. But also it should be followed with entropy growth. But for example, we live relatively close to the Big Bang, which had the low entropy, so it created this entropy growth we are observing. So, but fundamentally, the equation should be symmetric. So, and here are the examples. So, I'm talking a lot about these simulated emission absorption equations governed by these two equations, which are just symmetric, which will switch sides in CPT perspective. Okay, so maybe some philosophical slide now. So we have these two basic philosophies of time. One is this present, is that there is present moment, it evolves future time, but there is also this eternalized block universe that the four-dimensional solution is already there, and we just travel to the solution. And for example, for symmetry, we need this picture. There are many other arguments. For example, if we solve with the reduction principle of the Feynman assemblies, all of them are this symmetric, more symmetric view. So we should in fact use this kind of philosophy to understand physics. And there is a nice thought experiment that in general relativity, in theory, it could make wormhole which is non-orientable. Traveling to such a wormhole, it could switch the time direction inside a rocket. So a rocket with one quantum computer would get reverse one quantum computer inside. Yeah, so would be postparation and pre-measurement from our perspective. So in theory, there are many arguments that quantum computers should be thought in a more symmetric way. So we now think about it in an asymmetric way, state preparation, inter-evolution measurement, but physics in general should be symmetric, and in theory, this process should be able to reverse them, at least in theory. And I will show some practical approaches to do it. Okay, so having this reverse rocket, it would have this pre-measurement and postparation. But it still would be only as powerful as one quantum computer. This reverse one quantum computer. So to get something more powerful, we need two-way quantum computers. That we have both the state preparation and postparation. So we can affect both the initial and final states. So like in this Feynman path ensemble, that we fix the boundary conditions in the past and future, and physics assumes the Feynman ensemble of trajectories between them. Yes. So it is involved from framework. This is this kind of simple two-way quantum computer. Yes, with the state preparation, we can measure some qubits, and for some you can apply this reversed state preparation. So which kind of projection is after as post-selection, but has better success rate than post-selection, I mentioned in a moment. So mathematically, we can say that we get these two types of qubits. So one will be measured. So we perform this inter-evolution. We have some ensemble, and then we literally make projections on the second qubits, and we get some different ensemble. Yes. So now I try to convince you that mathematically it's the same, practically the same as post-selection, but with higher success rate. This postparation. Yes. So here is higher success rate post-selected one computers. So here is standard measurement probability. Yes, so you probably know where this formula trace of projection. So after this state preparation and some inter-evolution, some noise inside, we get to this density matrix law, and we treat it in three different ways. So the basic way is just measure, getting this probability distribution. We could also make a post-selection. So that means we have some additional condition C. So we have n qubits for the state and n qubits for this condition C. So we measure here in post-selected one computer, we measure both n plus m qubits and discard all but those which satisfy this condition C. Yes, so finally we get the probability of this being, so the C has to agree, and then we divide by this probability of this condition. So that probability that running the computer and measuring all the qubits, we get the condition as desired. Yes. So generally, this probability should drop exponentially with the number of qubits. So it's very bad. We cannot use it practically for a large number of qubits. So in two-way quantum computers, you get something similar as post-selection, but the success rate should be close to 1. So in theory, we could get exponential speed up. Thanks for that, for example, to solve the problems. Yeah, so that's the goal here. So the probability should be the same as post-selection, but there is no longer success rates. It should be close to 1. Okay, so maybe let's now look at some technology, physics. So one type of computer technology is simple quantum dots. So one direction are these position-based qubits. Yeah, so in which they can be just use impulse for this tunneling to chosen positions, and this kind of state preparation is trivial to reverse. Yes, we just use the opposite impulse at the end. And from CPT perspective, we get the ordinary state preparation. Yes, so for many type of processes, also in the superconductor, you just use some electromagnetic impulse, just use reverse impulse at the end, and it should act as the reverse version of state preparation. Yes. So there are also different types enforcing spin, but these are still just electromagnetic impulses, which in theory it's easy to reverse just in the controller for the computer. Yes. So this is, I think, interesting to test experimentally. Does it work as this reverse state preparation? Another type of technology, science fiction for now, but there are topological quantum computers, which are literally, which are completely symmetric. There are just these Feynman paths literally in space-time, and we can fix them in both directions. So they are naturally to make two-way quantum computer, if successful, but I'm not sure if they will be successful, but there is some progress in recent years. And I believe that the most promising direction is through optics. So often you like to start with excited state. So we have some optical pumping. So we like to, for example, use a laser to make it excited state. So here is some. So here is this so-called ring laser with optical isolator. Inside, the photons should travel in one direction. So in this setting, the photons should finally go here and excite this target. But if you look at this setting from CPT perspective, we believe that CPT symmetry is true. It would reverse the trajectory of photons, and now you should act on this target. Okay, so we have two equations. One increases the number of excited atoms, and the second of ground state atoms. So we have simulated emission and absorption equations. Yes, and they are switched in CPT perspective. So here we can make state preparation by optical pumping, while here we get again state preparation, but in CPT symmetry perspective. So we should get this postparation the same way. Yeah, so if here we can do state preparation, then here we have this CPT symmetry analog from the second state of laser, and I will show a few arguments for that now. Okay, so maybe you would say that laser can only excite external targets. So that only the absorption equation acts on external targets. But it's not true. There is also this second equation, this stimulated emission equation. And for example, there are this state microscopy, stimulated emission deposition microscopy, which literally excites some dot, then enforces the excitation around it to make a smaller dots, to get improve the resolution of the microscopy. So it uses both equations, this and this on external target. So we usually see only this equation, only excitation of target, because the N1 is usually very small. Usually we have mostly ground state target. But if we excite initially the target, then this equation becomes essential. Yes. So and here there is a three-state system, and it is excited by one laser, and then it can enforce the excitation, and it literally works. So both equations are in fact on the external target, but we usually observe only this one because N1 is usually very large, and 2 is excited number is very small, this is very large. In some other situation, unless we excite it somehow. Okay, so can we separate these two equations? Yes. So here there are used diode lasers. So in diode laser using steady state, both equations act on external target. But in this kind of laser, there should be only one equation, and it's switched in CPT perspective. So we should have kind of two types of forward and backward beam. One for this equation and one for this equation. So fractional optical isolator, we should be able to split the two equations, treat them separately. What should be useful for quantum applications. For example, having only these equations, there should be no, we should go to a fully excited population. So and turns out that there is similar relativism free electron laser. There is also only this one equation should act on, and indeed they try to search for the Rabi cycle for free electron laser, and despite theoretical predictions, instead this is the best article. So you can see that it goes to the excited state only. So in the Rabi cycle, you should go to 1/2. For free electron laser, they cannot get to 1/2. So it seems that they have only one equation, only absorption equation. There is no symmetric emission equation. So they can get near completely excited state with this kind of laser sources like free electron laser and maybe ring laser. That we can separate the two equations. So we have this Rabi cycle which both excites the target and also causes the excitation periodically. But here we have only one equation, so we don't have the cycle. So here is some summary of these two types of that finally laser. We have two types of equations acting on external target. So I call it forward beam causing excitation, but also there is backward beam. So in diode laser, for example, in state microscopy, both equations are at an external target. However, there are at least two ways to separate them. One is through this optical isolator. Second is through synchrotron radiation. And indeed, if you separate them, for example, in free electron laser, don't get a Rabi cycle. You get only excitation. Experimentally, there are few articles. So it is, I think, very interesting that you could prepare fully excited state using maybe ring laser with optical isolator. Okay, so here is the experiment. The very simple experiment I tried to organize. So the creation of this stabilized setting. So we have these three processes. Yeah. So we have stimulated emission, which increases entropy. So we have production of photon in random direction. We have absorption, but also from CPT perspective, this absorption becomes the reverse. Yes. So the photons should go the opposite direction. In contrast, in textbook, we get this picture that photon kind of knocks out the energy of single photon. So the question, which one is true? And I have mentioned a few arguments that I think this one is true. It's not the textbook one. Finally, I'd like to test it, and this is a very simple test to perform. That we have continuous excitation of this target system and impulse depletion. And we look at the detector which focuses on this spontaneous emission, and we just look at the line between the impulse and the impulse of the detector. And the question is, what is the sign? And I'd like to organize very simple. If somebody could help me, I think it's a interesting article to distinguish these two possibilities. So the more CPT symmetric and the textbook one. For example, for two-way quantum computers. Okay, so here is another view on this two-way quantum computers. So we have two-way treatment for electronic chip that connecting a chip to battery, it acts as kind of a pump. It both pushes electrons here and actively pulls electrons from the other direction. Also for hydrodynamics, so we have chip and we have pump, which both pushes with positive pressure and pulls with negative pressure. So the question is, could we take it to some electromagnetic photonic system? Yes. And so mathematically, electromagnetics and hydrodynamics are very similar. Nobody needs the same equation, especially using superfluid. So can we recreate this setting with microwaves or maybe photons? And I think this ring laser should allow for that. So here is this optical chip, and we have this ring laser which have only one type of circulation. So now it makes an impulse here, which is used often as a state preparation. But if you look at it from CPT perspective, the photon circulation will be reversed. So now it makes the same state preparation, but the opposite direction. Yes, so it uses both standard state preparation, but also symmetric version, postparation. Yeah, so why shouldn't it work? Yeah, so in synchronization is not simple, but in theory it should work. But we kind of both push and pull. There is also optical pulling. There is negative radiation pressure. So it should in theory it should work. Okay, so it was some physics side. And so there are obviously many technologies, and each technology should be thought separately. So we need to take a look at the state preparation process and think if you could reverse this process. So to make it that from safety perspective, we perform the state preparation process. So if it is just electromagnetic impulse, then it should be easy to reverse. Just use opposite impulse in the controller. Yes. Or if it's some optical pumping, I think it should be reversible by just, for example, using a ring laser, or maybe the rays. So okay, if being able, I think put fuel to quantum computing to allow for more powerful. Now let's talk about consequences like solving in theory and problems. Okay, so here are some complexity classes. So there are some polynomial algorithms, polynomial time algorithms. Then there is NP. There is polynomial time verifier. But there is exponential number of inputs, so we like to find the proper input, yes. And we complete, for example, 3-sat. Then there are p-space, also very interesting, like 3-sat, but there is also 4-all quantifier here. Then there are BB2P, to solve by quantum computer in polynomial time with some reasonable error probability. There is post-B2P by Alonso, so they are known to be able to solve any problems. And what I'm saying is very similar to this post-B2P, but maybe so I call it two-way B2P, but I think it should be the same as post-B2P, using this postparation, adding this operation of postparation. Okay, so let's now look at some algorithms. So here is the short algorithm. So a short algorithm. Short algorithm above, we prepare ensemble of 2 to the power n inputs. We calculate classical function, which is power in short algorithm. Then we measure this classical function and force it into one value. What restricts the ensemble to some periodic subset. Then we calculate this period from the transform, and we get some hint for our problem. Yes, this is short algorithm. So here you like here is Ising model approach that in theory in Ising model we could express the problems. There are many kind of approaches that in theory idea perfect Ising model in theory could solve the problems, but I don't think it's so perfect. So the Boltzmann ensemble there, I think it's only approximation, but in theory it is relatively simple to express problems in Ising model. There are some such articles. Okay, so here is such two-way quantum computer, very similar to this short algorithm. So also we prepare all inputs to exponential number of inputs. We use classical function for 3-sat for NP problems. This calculation of this verifier. So then, but instead of measuring then this value of this verifier, you'd like to enforce it to 1. Yes, so we'd like to make it that our verifier complete problem is true. For example, for 3-sat, we have separate alternatives, and we'd like that all the alternatives are true. Yes, so we could do it with post-selection. We could measure them and discard or situations where they are not all ones. Yes, so but it would cause the probability of success would be exponentially dropping the number of qubits. But having this postparation operation, we should be able to enforce these values of these qubits exactly as we enforce the initial values with the operation. So we should be able to enforce for 3-sat all the alternatives to be 1, and then measure some input, and it should be the solution to our problem. Yes, so in theory, you should be able to do it. Okay, so here is some short. So here is the same. So here is the short that we prepared all inputs. We calculate classical function. We measure this classical function. then this makes a restriction. Then we make Fourier transform to get this period, which gives a hint to our problem. And here is the same, but for example, here we can have the verifier and we try to enforce it to 1. So to make that this ensemble has only solutions to our problems. And here is some. So here is some. So yes, here is again that we have this the mark. Here we have the alternatives of TSAT, and there are some nodes here. And finally, we try to enforce all of them to 1. So the question is, there will be some imperfections. The question is if we can overcome these imperfections. That's the big question. So here is some ensemble. I think it should be practically observed that the imperfection, the more alternatives are negated, are wrong, the lower the probability. So there should be some. Okay, so I think it's doable to overcome these imperfections. So for example, we can also in theory make some better error correction. For example, we have this kind of gadget which literally enforces the 2 qubits to be equal. Yes, so we also have 0, 0, and it literally enforces 2 qubits to be equal. So we can make many copies of the qubit to improve the resistance error correction of such a circuit in theory. Okay, so here is the Groover article by Grzegorz Gustav. So here are some results. So here you would like the oracle, and here he has enforcing its final value, and you can see that there are three types of errors, and always when quantum computers such a probability is much larger than some other one. So it indeed should improve both the speed and the error resistance having these operations. Yeah? So if showing experimentally, this would be very important work, and others should work further on that, and should bring a lot of fuel to quantum computing. And so another question is, could we break no cloning theorem, for example, to try to attack some quantum cryptographic protocols? And turns out we cannot. That if this post-selection or post-paration, still the no cloning theorem works. So it's relatively simple proof that still the assumption that we can clone. We can show that lead to contradiction. So still quantum cryptographic protocols should be safe, at least from such attacks. But I think there will be other attacks from this kind of approaches. Okay, so I have finished the main part. So I have some extra slides. I don't know, maybe let's go to the discussion.
Please use your time. I mean, okay. I think you have more than enough, so please continue next 10 minutes.
Sure. Okay, so I have some other, maybe more philosophical directions to show the time symmetry, some this analogy with hydrodynamics. So maybe let me very briefly go through this slide. So for time symmetry, there are very nice experiments. For example, the Wheeler experiment. I don't know if you know that for example, if you have, imagine that you have a telescope, and you can go, your photons can go left or right of some planet on the way. And now the question is, can we distinguish the two possibilities? Obviously, this is the source, and this is your telescope or some detector. So switching between detectors, you can switch if they're between classical and quantum behavior. And there is the realization aspects that this hard mirror, hard secret mirror was, so this one was lifted or not. So if it's lifted, then you have classical behavior of photons. If it's down, then you have quantum interference. So photon here should know if this photon should behave as classical photon or quantum photon, but they make it after the photon went through it and it works. So kind of choosing between classical and quantum behavior photon after this choice was made. Yes, so for me, it's one of many arguments that we should think about this time symmetric view. That in fact, we live in a block universe, that the future is already there to the same extent of scenarios, and we just travel to them. Okay, so another very nice experiment asking photons where they have been by Weidmans and others. So here is so they use some vibrations for mirrors, and different mirrors have different, so selected vibrations. Different mirrors have different frequencies. So finally, they can see which mirrors were visited. Yeah? So they can ask photons where they have been, to which mirrors they have visited. And this is the most interesting setting. That if you look at the setting, they should see only C mirror, but they see also A and B. So that's the big question: why do you also see A and B, but the photons in theory does not travel to it? So the answer is that in fact we should use these two state vector formulas, that ABC are the only mirrors for photons going forward and backward in time. It's very nice experiment. Don't know it. I recommend looking. Okay, so another experiment are these quantum erasure experiments, and this is the nicest one I know by Valborn. That they have quite a wave. So literally they have setting that rotating this polarizer, they switch between classical and quantum and classical statistics behind this experiment. Yes, so rotating this, you can switch between this and this, and the second arm. So it's very, very non-intuitive, but it's crucial that you have to consider it. Without it doesn't. Okay, so here is some summary of what I showed previously. Yeah, so I think this is a nice thought experiment that in theory, general relativity allows to make this reverse one without computers by going to such theoretically possible non-orbital wormhole, which switches into postparation and pre-measurement. Yes, so I think this is a nice thought experiment. Also, it switches the two equations, the symmetric absorption equation. Yes, inside the rocket is the opposite. Okay, so also like naively laser heating, there's also cooling, laser cooling. Also naively is pushing. There's also many approaches to laser cooling. Also there is negative radiation pressure, because it works very similar to hydrodynamics. Yes, so the pressure is a vector. So if it's toward the surface, it's positive, but if it's out there, it's negative. So there is no problem with having negative radiation pressure. Okay, so there are some other approaches. Maybe let me skip it. Okay, so we can thought about this hydrodynamical analogs, maybe for tests. Okay, so maybe talk about this analogy between hydrodynamics and electrodynamics. So we can have both positive and negative pressures. So there are a few ways to do it, but the equations in fact are very similar between hydrodynamics just superfluid when we say that viscosity is 0. And there are very nice experiments that this Aharonov-Bohm has hydrodynamic analogs. So half of them are for Aharonov-Bohm, half of them are for hydrodynamics. They are hard to distinguish. And there are these very nice bouncy droplets experiments which are able to recreate, for example, quantized orbits. So we have some fluid, and it vibrates, and there is bouncy droplet which creates coupled waves. And for example, they get a double slit experiment this way, or the quantization that there is not any radius, but only some discrete ones, because the coupled wave has to become standard. So there is one condition which agrees with the all the quantization. And moreover, using this analogy between hydrodynamics and electrodynamics, the Lorentz force becomes the Coriolis force. And indeed, just rotating clockwise or anti-clockwise acts as the Lorentz force, and they get this Zeeman splitting. So they are quantized, and they get Zeeman splitting using Coriolis force as Lorentz force. Yeah, so it's just that this analogy with hydrodynamics is quite deep. A few examples. Okay, so at the end, so maybe one slide about that this symmetry is crucial for this Born-rule evaluation. So the question is the big problem with quantum mechanics is that we have this Bell theorem says that they can be localized model. Yes, so why it is so? So again. I think it comes from this time symmetry, but in fact, at a given moment, it's kind of in equilibrium between past and future. So, for example, here we have a standard random walk that we have a Boltzmann ensemble of single steps. So for 0-1 range, it leads to station hypercomplex distribution being uniform in this range. But if we use ensemble of paths from now to our future and to our past, then we get sign, station hypercomplex distribution proportional to sign. But if you use full paths, symmetric from the past and future, then you get sign squared. Because to get randomly given position, we need to randomly get it from past and future. Yeah? So it is also in Ising model that at the end of sequence we have amplitude, and inside to get randomly some value we need to get twice from left and right. So we get the Born-rule exactly, and we can use it for example for Bell evaluation with Ising model. So there is this simpler than Bell's inequality, this Mermin's inequality that tossing three coins at least to give the same. It looks very intuitive. However, quantum mechanics in theory can validate it, and also Ising model. So to derive this inequality, like here, we have three coins. Yes, ABC there are coins, so we have 8 possibilities. Whatever is joint probability distribution we assume. So this probability of A by B corresponds to these 4 possibilities. This for 2, this 4, this 4. If you sum it, then we get at least 1 everywhere. So it has to be at least 1 because all probabilities, all 8 probabilities have to sum to 1. Okay? So we have proven this inequality using common axiom, that probability of AB question mark equals probability of 0 or 1 on this on position. In contrast, quantum mechanics replaces this common axiom with the Born-rule. Yeah, so we add amplitudes and then make it square. And also in Ising model. So here is a way to validate this inequality in Ising model. You have sequence of 3 spins with interactions forbidding these two possibilities. This all up and all down. So we have at the end of such Ising sequence, the probability is 1/6 probability uniform over the remaining possibilities. But to get some values randomly inside, you need to multiply. You get it twice from the left and right. So we have to get this Born-rule also in the Ising model from Boltzmann ensemble, and we get 0.6. We validate this inequality 0.6. Yeah. So we get the Born-rule from time symmetry that in fact in this moment is intersection between past and future. So to get some value, we need to get it twice from the past and from the future. So and also we can do it in Ising model. So Ising model replaces Hermann ensemble with Boltzmann ensemble. So it's very similar to quantum mechanics. Yeah, so again, we get the Born-rule because at the end we get the amplitude. In the center we have square amplitude because we need to have get it randomly twice. So again, the time symmetry is extremely crucial for physics. Okay, so maybe let me skip. So going back to quantum computers, there are many techniques, and all of them have to be discussed for this reverse state preparation process. And maybe let me finish. Yeah. So if somebody would like to discuss it, and maybe collaborate like this, adding into controllers reverse impulses for state preparation, one direction, or I have a few approaches for tests with lasers.
Okay, great. Thank you, Eric, for the great presentation. Thanks. Okay, let's move on. Okay, do we have questions? Yes.
Yeah, can you make a summary? Because actually, I would say it's not always that easy to follow your talk due to tremendous amount of
Just
information.
trying to convince that in theory physics should be symmetric and we should be able to exploit it.
Okay, but can you write on the whiteboard, let's say, the CPT, no, the blackboard, sorry. The CPT is broken, then what? Can you make a 3-point summary on the...
Okay, so assuming CPT symmetry is true, and most physicists assume that it's true, yes.
It's true, so most physicists assume that CPT symmetry is true,
Yes.
both at microscopic and microscopic and
Exactly.
micro and macroscopic level.
But it is tested only in macroscopic settings. So this can be also seen as a test for macroscopic situation.
Okay, so you offer the test of CPT symmetry on macroscopic level. This is what you offer, right?
Yes.
And what happens? So your two-way quantum computer will work under the assumption that CPT symmetry is
fine for all states.
both on macroscopic and microscopic level. So your two-way quantum computer is working there. If it does not work, it means that CPT symmetry is broken at microscopic state. This is what you imply.
This type of test from one side would allow for new applications like wave computers, but even if they are not successful, they show the relation CPT symmetry.
All right. Okay. So basically, there are two main paths that comes from your talk. First path is fundamental experiments about foundations of physics, which test validity of CPT symmetry. That's the one path of your in essence motivation. And second path of your motivation is a further contribution to the development of quantum computation, right?
Yes, but they are separate problems. Yes. So if CPT symmetry is validated in macroscopic scale, then this approach might not work. But if you
well, separately or not separately, but I still believe there is some level of interconnection. So you basically imply that two-way quantum computer will have better computation efficiency than classical known quantum computer. What is the speed up factor?
So exponential.
So you think that your proposal of two-way time, like 2 arrows of time quantum computer, will have an exponential speed up in comparison with well-known quantum computer, right?
Yes, exactly. So there is a success rate which drops exponentially, and it should be 1 for
All right. So you basically you in a sense propose further enhancement of quantum computation, and then you basically search for possible collaboration from some sides, as HCS or Japan or anybody else, and then you want to construct a framework of new experiments, right? That will validate your claims or will confirm or reject your claims.
Yeah, so basic two ways are taking standard quantum computer and trying to reverse the impulses used for separation. Yes, this is one direction. And the other direction is using laser and testing this limited emission absorption equations.
Okay, lasers. So in case of lasers, do you propose lasers on small scale or on a big scale?
So the simplest experiment for lasers is this one. Yeah. So just 2 diode lasers and measuring the distance.
But that doesn't mean that this is a laser on one chip.
So no, just microscopic lasers.
No. But be specific about the size. What size you need?
Standard diode lasers.
So the diode laser, is it a ring laser? Is it a ring laser or just?
So no, here is so the next step could be ring laser. So I think the ring laser allows to split the two equations. So if then you replace this impulse separation laser with ring laser, if you use the standard forward beam, I think it shouldn't work. because there is no equation for this emission. But if you use this backward beam, which is ignored now, so if you use this forward beam, it shouldn't work for depression laser, but if you use this beam, it should work. So,
oh yeah, I think it's the best to discuss more details during today's panel discussion that starts at 7:30, right? Is there anybody else with any questions?
Yeah, thank you. I have a short question regarding the two-way computing. Could that be expressed in a high-level language like Qiskit? Or would you need a hardware change in order to implement it?
so
Because that's, I mean, if you could do it in Qiskit, you could basically do it and test it on any existing quantum computer.
yes. So yes, it's a very good question. So for some frameworks like Wolfram quantum framework, you can directly use super dagger of state preparation and let's say this revised version of state preparation. If there is not, then you can use postselection 0, 0. Yeah, so it should work the same, but just using 0 operator for postselection, it should work the same, but it lower success rate. But mathematically, it should be the same.
There are no questions.
I'm afraid I have many questions, but I will try to summarize two basic things. First of all, if I get correctly, we get some kind of symmetry between inputs and outputs. So my question is, this is a more discrete symmetry. What about conserved quantities? I'm thinking of another theorem, and could we get some extra info about it thanks to this symmetry? And I will ask my second question also. You mentioned that this could improve things in the polynomial order NP space, but it's something strictly on NP above, strictly on P space, or something in between. It's not.
Yes, so the second question is, I'm not certain. So I think it's the same as post BQP, and it goes above NP, but I think it's below P space. So some between. Really, the first question, I think generally yes. Also, you should look at everything mentioned separately. Yes, so it's technology. So, for example, for simple quantum dots, it's like reversing the totality. So it's trivial. So I don't know what we should test consecutive quantities here. And for this laser based, you have a laser with single circulation of photons, and from symmetry perspective, you just reverse the circulation, and you should switch the two equations. So I'm not sure what kind of conservation you want to.
No, I just hoping that as we have continuous symmetry implies conserved quantity, here we have a discrete version because we can say past future models we can solve. So maybe we have some topological protection or some smaller.
I'm not sure. I think it's open the question, but generally you look at the same setting from perspective of symmetry and try to prepare it such that you perform the state preparation process. Yes.
Okay, we have no questions. Yeah. One more.
What basic parts are photonic? Of what basic parts is photonic chip made of?
So okay, I have some better image from some paper. The slides are available in my. So here is some analytical in this link. Slides. So here is, so you can see that here there are SPDCs done professional. There are four photon analysis. So here is kind of Hadamard. Then you have the gates. Finally, made the measurement. But usually they start with impulse. So the question is, could you make the reverse impulse at the end? And there are these ideas like here, yes, that you have this kind of pump for photons. But if you look at it from symmetry perspective, then you reverse that. So now you perform the impulse here, but from symmetry perspective, you perform the same impulse from the end, applied to some of qubits. But you can reverse this input. So you that from simple perspective, you make the same as here from some to this again.
Oh, okay, and gates are made of, I don't know, light meters or.
Yeah, I'm not certain, but yes, so there are some lithographies that they are able to make some yes.
Okay.
Okay. Do you have more questions? I'm not sure if you actually have time for more. Maybe someone from Zoom would like to ask.
So now the interns from the Q-Inter program just present, I see one of them in the class.
But they will be later, right? So,
In fact, in 8 minutes.
Yes.
In 8 minutes.
So can I give my presentation right now?
Oh, you should. So
I wanted to still give you more time because I know that your talk was very condensed.
Sure.
So that's why I tried to expand your time because it's better for the audience.
So
Can I give my presentation right now or?
So in theory, there should be this 2 hour window for now for the students, and not I see only one of them, but I could.